Welcome, everyone. Thank you for joining us for today's webinar, Use of Gas Chromatography for the Analysis of Cannabinoids and Terpenes. It is presented by Allegra Leghissa, PhD, a postdoctoral researcher at the University of Texas at Arlington. My name is Judy O'Rourke, and I'll be your moderator for today's event. We're delighted to bring you this educational web seminar presented by LabRoots. LabRoots is the leading scientific social networking website and producer of educational virtual events and webinars. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want during the presentation. Simply click on the Ask a Question box located on the far left of your screen and type your questions into the drop-down box. Our speaker will respond to your questions via email following the presentation. If you have trouble seeing or hearing the presentation, please click on the Ask a Question box to let us know that you're experiencing a problem. This presentation is educational and thus offers continuing education credits. Please click on the Continuing Education Credits tab located in the top right corner of the presentation window and follow the process to obtain your credits. Now, without further ado, please join me in welcoming Dr. Leghissa. I will now turn the presentation over to her.
Hello, everybody, and thank you very much, Judy, for the introduction. I'm Allegra, and as mentioned earlier, I'm going to be talking about the use of gas chromatography for the analysis of cannabinoids and terpenes. But before actually getting into the research itself, I would like to give a small and brief introduction about cannabis sativa and its analysis, about cannabinoids and terpenes, and also about gas chromatography. So there can be a basic knowledge of what I'm going to be talking about. So as we can see from this little diagram, there are mainly 6 different types of analytes that researchers want to study in cannabis sativa. Cannabinoids that are the main components of the plant and are the chemicals that give the psychoactivity and the medical benefits. Terpenes that are actually not only found in cannabis sativa, but pretty much in all types of plants. And those are the molecules that confer fragrances and aromas. And then we have 4 different types of 4 other kinds of analytes that they are called actually contaminants. So ideally, they should not be present in the plant. And we have pesticides, solvent residues, heavy metals, and microbes and toxins. So as you can see, under each name of the analyte, I highlighted the different methods that are most widely used for the analysis of these analytes. And we can see how terpenes, cannabinoids, some pesticides, and all solvent residues can be analyzed by gas chromatography. So this is one of the main reasons why, in my opinion, having this instrument in a cannabis either research or even quality control lab is extremely important. So gas chromatography, as the name itself says, is a type of analytical method that will analyze all molecules in a gas phase. That means that the sample does not actually have to be found in a gas phase. Actually, most of the time, it's either in a liquid or in a solid state through headspace injection. But what means is that the injection port is at such high temperatures that all the solvents and all the analytes are then going to be volatilized in the column itself. So to perform this type of analysis, of course, we require analytes that have lower boiling points, and the separation itself is actually based on the boiling, or more accurately, the dew point. And we can see in here the chromatograph that we obtained on the bottom left, a chromatograph that we obtained by analyzing and differentiating delta-9 THC and its 2 main metabolites. I'm not going to talk about this in today's presentation, but I just wanted to give you an idea of how normal scan chromatogram in gas chromatography work. So as we mentioned earlier, gas chromatography is perfect for the analysis of cannabinoids, terpenes, all residual solvents, and some pesticides. So cannabinoids are the main components of cannabis sativa. This plant has been reported to have over 100 different species of them, and because of that, and based on their structure and their properties, they have been divided into 10 different classes. As we mentioned, they confer psychoactivity, especially delta-9 THC, that is the main psychoactive cannabinoid, but also the medical benefits. And the importance for the analysis of cannabinoids in the plant is not only for potency. Potency is what we are actually calling the level of delta-9 THC, but also to understand the therapeutic effects that each different strain can confer, but also trace analysis. Trace analysis meaning, for instance, whenever you're purchasing a CBD oil, you want to make sure that allegedly there is no trace of any other type of cannabinoids in the extract. So we said that there are 10 different categories of cannabinoids, but for the purpose of this research, we solely put our effort in analyzing the 8 different cannabinoids that you can find at the bottom of the slide. Of course, we have delta-9 THC because we mentioned that it's the most psychoactive cannabinoid, and it has always been the cannabinoid of most interest. Then we have its isomer, delta-8 THC. The only difference between these two molecules is the position of the double bond between 8,9 to 9,10. And we have delta-9 THCA. It's the acidic component that is the precursor of delta-9 THC. This molecule is actually extremely tricky to characterize by GCMS because the carboxyl group that you find on the phenyl group is highly labile at the temperatures of the GC injector. And therefore, what happens to this molecule is that it gets degraded. This carboxyl group gets kicked out, and so delta-9 THCA is transformed to delta-9 THC. This will lead to both negative because no delta-9 THCA will appear on the chromatogram, but also false positive because the amount of delta-9 THC is going to be detected higher than what actually is found in the plant. So for this reason, the analysis of cannabinoids via GCMS actually needs to be done after a derivatization reaction, mainly silylation. And this type of reaction will actually protect the carboxyl group, avoiding its decarboxylation. Then terpenes are the second most important components of cannabis sativa, but as we mentioned, they are found in any plant. And in nature, there have been reported more than 50,000 different types of terpenes, but cannabis sativa has been reported to have solely 200 of them. And they confer odor and fragrances. For instance, limonene is the terpene that characterizes the lemon peel and confers that odor. But some of them, such as beta-caryophyllene, have been reported to actually have some therapeutic effects. So as you can see from the 3 bottom structures of 3 different terpenes, their chemical structure confers them a pretty high volatility, so they are perfectly suitable for GC analysis. And as of today, 3 different types of detector have been mainly used for the analysis and the determination of terpenes. But all of them may have pros and cons. So for instance, flame ionization detector is excellent for quantitative analysis, but is not so reliable for the qualification of terpenes because their distinction is solely based on retention indices. Mass spectrometry at the same time, in the same way, is great for quantitative analysis, but even in this case, the speciation between terpenes is done solely by comparison to standards and the retention indices. And then finally, there is this new, fairly new technique called the vacuum ultraviolet detector. It has been developed around 2009. And it's good for quantitative analysis, but it's not as sensitive as the other 2 detectors, but it's extremely reliable when used for qualification because each molecule is going to give a specific and unique absorbance spectrum, even when talking and analyzing isomers that may be tricky with the other 2 detectors. So now I'm actually going to start talking about the projects that we did throughout the program. So the first part is the analysis of cannabinoids on GCMS. So we saw earlier what different types of, why cannabinoids are important to be studied. And I mentioned the trace analysis. So this type of method will actually give extremely low limits of detections. And for this reason, this method is not suitable for potency testing, but it's We have used it for trace analysis, and so to check whether other components were found in CBD oils or in other types of extracts. So in these slides, these two tables only describe the different types of conditions that I used. The table on the left shows and describes the silylation reaction, as we said earlier. The silylation agent that we decided to use is BSTFA, that is represented in its molecular form structure is represented at the bottom of the table. And we use the 1% of TMCS as a catalyst. The procedure is pretty fast and straightforward. So the standard was dried of the solvent with a stream of nitrogen at 50 degrees. And then 50 to 50 by volume of ethyl acetate and BSTFA plus the catalyst were added, and everything was incubated at 70 degrees for 30 minutes. This is not extremely necessary, but we did it to speed up the reaction. And then before the injection, everything was cooled down. While on the table on the right, we actually see the conditions used in the gas chromatographer. It's a pretty standard separation. We used a polysiloxane column. The polarity was not really high. As you can see, it's only 5% diphenyl dimethyl. And we used the splitless injection. And we coupled it with the Shimadzu triple quadruple detector. So the triple quadruple is, as the name says, it's created by putting 3 single quadruples in series. So all the different ions that are formed in the ionization source, in this case electron impact, they are passed through the 3 quadruples. And different modes can be used with that. So the mode we used in this experiment is called the multiple reaction monitoring. So I have a short animation to explain that. As you can see, we have on the left of the slide 3 different balls with 3 different colors. So in real life, these balls represent different ions from the same molecule that are formed in the ionization source. So once they are formed, these ions will start passing through the first quadruple that actually works as a filter. So it will allow only one ion, in this case, one ball, to pass through the second quadruple. The second quadruple is not a filter, but is a fragmentation chamber. So the ion that was allowed to pass is going to be further fragmented by a stream of argon gas, forming different product and smaller ions, in this case, these smaller balls. And these smaller balls are then going to pass through the third quadruple that is going to be working as a filter, just like the first one, allowing only one ion to pass and to reach the detector. So the result is that we get really high specificity and high sensitivity compared to the other modes. In here, I'm actually showing 2 chromatograms that we obtained with the MRM mode. The one on the top is the underivatized cannabinoids, while the one on the bottom is the silylated cannabinoids. So many differences already pop up. First of all, of course, the absence of delta-9 THCA in the underivatized chromatogram, but we already explained why. Then we can notice how the retention time for each cannabinoid shifts, whether they are underivatized or if they are silylated. For instance, cannabinol, that is number 7, when it's underivatized, so it's in its natural form, it's going to elute at around 19.75 minutes, while once it's derivatized, it's going to elute at 17.5. And this is because the silylation not only protects the carboxyl group, but also lowers the boiling point. And the last difference that we can see is how the 2 cannabinoids, cannabichromine and cannabidiol, number 2 and 3, were coeluting in the underivatized chromatograms, but in the derivatized chromatogram, they pretty well separated. The reason why this happens is because each cannabinoid, based on their chemical structure, have different numbers of available silylation sites. And this leads to higher structural differences that will, of course, lead to further differentiation in the gas chromatographer. So this table actually shows, on the other hand, how we are going to talk and describe the multiple reaction monitoring results. We call it a database. So I have the database also for the derivatized ones, but for the purpose of this presentation, I'm just going to show one of them because it's a huge set of numbers and it may or may not be extremely interesting in the long run. But as you can see, so we talked earlier about the first ion that is formed in the electron ionization, in the electron impact source. And that is going to be in, for instance, the first column called the quant ion. It's going to be the first number on the left, for instance, 203, 231, and 31, and at the end, 295. So that is the first ion that is allowed to pass through the first quadruple and reach the second one. Then the number on the right of the equation, like 174 and 238, represent actually the product ions, so the ones that are formed after the fragmentation with argon and that are passing through the triple quadruple. And this number represents the only one out of all the different fragments that is allowed to reach the detector. So you can see how there are 3 different columns that describe 3 different transitions for each cannabinoid. And in many experiments, only one transition is enough to actually specify and differentiate among different molecules. But in this case, once we were studying the results, we saw how all the cannabinoids between CBD and CBG actually share the same transition. So we decided to use even the second transition to further differentiate among them. And there is a higher differentiation, but we can still see the same transition for CBD and delta-9 THC. So this is the reason why we decided to pass to the third transition. So in this case, by using 3 transitions, we decrease the sensitivity, but we increase the specificity for each cannabinoid. And another thing that we started, of course, looking at because of all these similar numbers is that some of these fragments must be extremely stable in the mass spec. And even if cannabinoids do not start from the same molecular weight, so even if they are non-isobaric, they may end up forming the same fragment. So we decided to further investigate, and we started speculating about what could be happening in the detector and why some of these fragments may be forming. So this is actually still a work in progress, but in here I'm just going to show you how, for instance, the fragment 231 is formed not only by delta-9 THC and CBD that are isobaric cannabinoids, but also by cannabigerol that is non-isobaric. Then from there we get different fragments from CBG, but I think this is an extremely important and interesting point. So for the work in progress that we're still doing, we decided to compare these transitions and this fragmentation happening in the GC to what may be happening in the LC with different sources. So hopefully that will be done soon as well. But yeah, as we mentioned earlier, this type of mode and this type of separation is really useful for trace analysis because the limits of detections that we get is picograms on column that are way below what we are actually going to get in the plant. So this method could be used for potency testing, but it would be a waste of instrumentation, in my opinion, and a waste of research time. So for talking about potency testing, we then decided to use the instrument that I mentioned earlier, talking about terpenes, and couple it to the GC. So GC coupled with vacuum ultraviolet detector. So briefly, I'm going to introduce this new detector. You can see the picture on the top of the slide, and then there is a diagram in the bottom of how it's actually built. The detector itself is not extremely big. It's pretty much this long and this wide. So the vacuum ultraviolet detector is called like that because it analyzes each molecule that absorbs between 120 and 240 nanometer. So it includes even the vacuum ultraviolet part of the spectrum. And as we mentioned earlier, each different molecule is going to give a unique absorbance spectrum. So even if two isomers are being analyzed, we can easily differentiate between them. And this is why we say that it's complementary to the mass spec, because as we saw earlier in the mass spec, isobaric components get fragmented, but in a similar way, while in here, and as you will see later, even delta 8 and delta 9 THC, even if their difference is only the position of the double bond, they have extremely different absorbance spectra, and so they can be differentiated. And my favorite capability of this instrument is the convolution of co-eluting analytes. So we will see how it's not so important to perform and to obtain a perfect chromatographic separation, because the difference in the absorbance spectra of each analyte can actually be used in post-run to separate the two co-eluting peaks. So for this reason, the GC coupled with the VUV is ideal for the analysis of both terpenes and cannabinoids. And you can see in here the first analysis we performed with underivatized cannabinoids. So just like before, we analyzed 7 of them because delta 9 THCA can be analyzed only if silylated. And you can see on the right, there are the different absorbance spectra. So as you can see how different they are. So you can clearly differentiate between the different molecules, but also because they all belong to the same class of chemicals, you can see how they pretty much follow a similar pattern, with one absorbance maximum at around 180 and one at 210. So by looking at this image, you can already pretty much understand how these unknown compounds fall under the same class of chemicals. While on the left, we have the chromatographic separation. As we saw earlier with the GC-MS, cannabidiol and cannabichromine are actually co-eluting. But in this case, it's not a problem, because the deconvolving power of the GC-VUV is going to take the two absorbance spectra of the two co-eluting peaks and subtract it to the co-eluting peak. In fact, once two peaks are co-eluting, the absorbance spectrum of the co-eluting peak is actually the sum of the two singular peaks. So in post-run, it's extremely easy to differentiate among them. And you can see that in the bottom right chromatograph, it's a part of the chromatograph, yeah, how the co-eluting peak is actually being separated into CBD and CBC for quantitation and not only qualification. Then we performed the analysis on the derivatized cannabinoids as well. So already you can see how we added delta 9 THCA, and how CBD and CBC, once derivatized, are actually further away from each other. And most interestingly, on the right side of the slide, you can see how the absorbance spectra are changed compared to the non-silylated cannabinoids, and how more different they are between each other. So if on the one hand, the GC-MS analysis was done and more suitable for a trace analysis, this type of detector is perfectly suitable for a fast potency testing. And now for the last part of our research project, we examined the different terpenes that we can find in cannabis on GC-VUV. Well, actually not all of them, but we just chose a handful set of them. And first of all, I want to highlight, even in the case of terpenes, just like with cannabinoids, you can already pretty much group the terpenes into different classes based on their absorbance spectra. So you can see how similar they are based on having only one double bond, or having two double bonds, or being oxygenated with double bonds. So even if it's not exactly known the structure of the terpenes, by just having a quick glance at their absorbance spectrum, we can already identify in what type of class they are going to fall. And even this one is actually a work in progress. So you will see in here the first chromatographic separation that we obtained, that is 45 minutes. We are actually fastening it to 10 minutes. And we are even trying to get the best extraction technique, because this is actually what is extremely challenging about terpenes analysis. There is not a validated, efficient extraction method. So there are different extraction methods, but none of them has been reported to be perfectly suitable for each type of application. So you can see in this type of chromatogram how the standards of terpenes were separated among each other. And you can see how the peak at 25 minutes pretty much looks higher in intensity than the other ones. And this is not because of the higher concentration of this terpene, but it's because it's the coelution of two different terpenes, camphor and isopolygol. So just like what we did with cannabidiol and cannabichromene, in post-run we can actually differentiate between them. So as I mentioned, this analysis is still a work in progress. We are developing the most an efficient extraction method of terpenes by using headspace analysis. And we are cutting down the analysis GC time to 10 minutes. And we hopefully are going to be validating this method soon. But even once this method has been validated, the road for fully understanding and characterizing terpenes is really long, because we all know that terpenes are naturally found in chiral forms. And these different chiral forms, these enantiomers, they are extremely hard to separate. You need a special column in GC that would be cyclodextrins. And they have, because they have identical properties, but they may have different medical benefits. They have different fragrances. They have different odors. So alpha, the two different enantiomers of alpha pinene may be extremely different in the properties among each other. And this is why it's important to actually differentiate and quantify both enantiomers and not only alpha pinene. So once I said that, I would like to thank everybody for being here today and listening to the presentation. And of course, I would like to thank everybody in Dr. Schug's group for their support throughout the years. I would like to thank the University of Texas at Arlington, and also Shimadzu Scientific Instruments, Reste Corporation, and VUV Analytics for the instruments and the consumables that were given to us for this project. So thank you very much for your attention. And if you have any question, you can either type them in now or send, I left in here my email address, so feel free to send an email anytime. Thank you very much.
Thank you, Dr. Leghissa, for that informative presentation. I would also like to thank LabRoots for making today's educational webcast possible. Before we go, I want to let everyone know that this webcast will be available for on-demand viewing through June 28th, 2019. As a final reminder, our speaker will follow up with any questions you've submitted via email. That's all for now. Thank you for joining us, and we will see you next time.